Thank you. Hi, I'm Chris, and I will be talking about bringing the power of C++ to the web. Let's start with a simple quiz, with a quick question. Do you know how many websites were existing in 1991? Yes. It was just one. It was invented by Tim Berners-Lee and announced in August 1991. Do you know how many websites we have today?
More.
Just slightly more. There are 1 billion websites available. Though out of this number, 400 million are active websites. And out of the whole population, more than 4 billion people are using internet. And this is more than half of the population already. And now we start to talk about the next billion users which are coming to the internet. And what if we could take some use of it? What if C++ could be run on some of these pages and some users could use of it? I think this is a great opportunity for the language itself to grow, but also for the community to grow. But in order to understand where we are now, we need to take a quick look into the history and see how the speeding up of web evolved over the time. So at the beginning we have ActiveX, which was a Microsoft technology. It was not intended to be Microsoft specific, though in practice it ran only on Windows, and even worse, it was compiled to the 8x86 architecture. So it quickly died, and now I think nobody even hears anymore about ActiveX. Then we've got Flash from Adobe Flash. Maybe you remember Adobe Flash Player. It was the platform for multimedia, for playing animations or videos. Now it is mostly deprecated as well. Then Google had its native client. A native client was a platform or extension to the web browser to run a native code within the browser. They also had an extension to the native client, which was the portable native client, and they claimed that this is architecture independent. Then there was another direction taken, and we got Asm.js. And Asm.js is a subset of a JavaScript language. What they did, they took everything which is quick from the JavaScript specification and applied the Asm.js. So as the result, Asm.js is more or less half the speed of the native. And since a couple of years, we have WebAssembly. And WebAssembly, it is often abbreviated as WASM. It's a binary instruction format and a language for a stack-based virtual machine. This is when we compare it to the Java virtual machine, which is both a stack-based and a register-based stack machine. So stack-based is in general simpler. So this is a binary code which can be compiled or executed by the host, by the client. That's what was the intention for WebAssembly. It is designed to be close to the bare metal as much as possible and therefore efficient. Also has a human readable form, so it is possible to write WebAssembly by hand, though it's not really recommended. And what's important, it is developed by a consortium of the companies and the communities. So biggest vendors of the web browsers, they sit down together and they started to work on the specification. So when you compare it to the Java virtual machine, which is owned by Oracle, this is a big step forward, that not one company owns the technology. That's a strange thing here, because WebAssembly is not really only web, and it's not even assembly. It's not web because it can run outside the web, so it goes way beyond the web technology. And if you think about it deeply, it's not even an assembly, because if you understand assembly like a set of instructions which are run on the raw CPU, on a raw processor, it's a raw machine instructions, this is a bytecode here, which is WebAssembly. So there's not much left of the name. Maybe you remember a JavaScript, which has actually nothing to do with Java, but we got JavaScript. So I think that people should work more on finding the proper names. Going to the philosophy, when the Java was released by Sun Microsystem, they coined a phrase, write once, run anywhere. just to illustrate that there is a cross-platform possibility for Java language. However, for WebAssembly, I like to say more that this is compile once and run anywhere, just to underline that this is a binary format and not something which is interpreted, for instance. And it's not only about C++. Though from the internet you could get an impression it's primarily about C++, it is actually about many languages. So with today's compiler's modular architecture, it is relatively easy to extend existing infrastructure with a new language. So if we take here a kind of LLVM approach, then we could have multiple languages, and for which we have the front ends, and if they can be compiled to LLVM bitcode, and we have the WASM backend, then we can get the WASM binary. And note here that I have a C, C++, and Rust. There could be much more languages actually. However, WebAssembly as of today, it does not support the garbage collection languages. So in fact, it is possible to run, for instance, a Kotlin or Go, which are garbage collected languages, in the WebAssembly. But what one needs to do is to take the garbage collector itself and compile it to WebAssembly and then run it next to the WebAssembly module, which is suboptimal. But for us as a C++ programmers, enthusiasts, this highlighted path is the most important. And I think we need to stay focused because, as I said at the beginning, this is a huge technology and it has a lot of potential in it. However, it looks like that at least for the new code, there are other languages which are used more than C++, especially Rust. So I think as a community we need to work harder in order to popularize C++ within this field. I think it's not yet too late, but soon it will be too late, and C++ will not head in this race. So that was about the flexibility on the input side, so on the language side, that which one can use. But there is also flexibility on the other side. So once we have a WebAssembly binary, it actually does not matter how we run it or where we run it. So as of today, it can be run out of the box in the 4 major browsers like Firefox, Chrome, Edge, or Safari. But there are also attempts or the projects to create a WASM runtime, which can be then run on the operating systems, so outside the web browsers. So that's also what I say, compile once, run everywhere. There was a tweet by Solomon Hykes, and Solomon Hykes is the creator of Docker. And he says that if WASM and WASI existed in 2008, we wouldn't have to create a Docker. And that's how important it is. And he even goes further and he says that he believes in the future WebAssembly will be used also on the server side. Again, maybe you remember JavaScript, and JavaScript was intended to be running on the web, but these days it's also taking over the server-side computations with the Node.js. So that's another possibility for WebAssembly to spread. He mentions in his tweet about WASI, and WASI is a WebAssembly system interface. This is a specification according to which the WebAssembly can be run outside the browsers in a secured manner, so sandboxed manner. So it's an abstraction module to access OS primitives like memory management or a file system. So it's supposed to be an efficient and safe runtime bridge between WebAssembly and operating system. As of the applications, we can split them into 2 classes. First class is a new code, new applications, and the other class are existing applications, so the old code. And for the new code, what's emerging today is distributed computing system in general and distributed ledger technologies in particular. So it's about more deterministic systems. So if you know about the Ethereum project, then you may hear that they have their own virtual machine called EVM, Ethereum Virtual Machine, and this has a lot of design issues itself. So the Ethereum team today, they are working on a specific WebAssembly virtual machine, which is a subset of the generic WebAssembly, but made deterministic. That means that they have a special handling for the floats, which can deliver different results depending on the hardware which they are run. And this is, of course, not something that we want, especially for the finance systems. On the other side, we have the Web3 movement. And the Web3 movement, it is about a more decentralized internet, more decentralized networks. So if you think about all the devices which are now interconnected globally, which is the billion of the devices, and they are not really using all the computational power that they have. So if we have a uniform possibility to access all these processors and execute them, then we can think about the global computer, which could work similarly to today's cloud computing. So today's cloud computing, the few providers, they have server farms in a few places in the world, when compared to this approach where you have more like a serverless architecture, so there are many small servers doing the work. Example is the project The Definity, which is working on this global computer thing. WebAssembly is primary for the big web applications. So good example here is graphical applications. If you know Figma, it's graphical applications which is running entirely on a web browser. So you can just try it out without installing anything. Of course, web games are the big part of the new code, new applications. And for C++, what also matters is that we have a lot of libraries which are already very high quality due to the decades of development, and it would be pity not to use them and reinvent the wheel in other languages like JavaScript. So for instance, we have an existing libraries like an OpenCV, which is a graphical library, and this project today allows to compile OpenCV down to ASM.js or WebAssembly and be run on the web. And existing native applications or frameworks, they also start to port today to WebAssembly like AutoCAD or Qt. And of course, game engines, so Unity and Unreal, they are all now attempting to trying to compile to WebAssembly and see how it works, where it goes. One thing which is not fitting exactly to these two classes I mentioned are PWAs, and those are progressive web apps. Today, user of the smartphone, of the mobile devices, they have two choices. They can run an app via the web app, or they can install a native application. And users, they don't really like to install the native applications because this is a commitment from them. This is also a struggle to install a native application. However, on the other side, the web applications, they are not as flexible and as powerful as the native applications. So progressive web apps is a hybrid which is somewhere in the middle. So we take the web browser and we run a web app on it as it looks like a native application. So this will be probably also a big share in the mobile market and a good chance for a C++ to have part of it. So from the presented applications, we already can see some properties like portability, flexibility, and speed. Those are obvious, and everyone is talking about it. But WebAssembly specifically is not for small modules, but it is designed to work well with heavy web apps. That's because, as of today, WebAssembly is running within the JavaScript. So if you think about a small algorithm or a small job you want to do in WebAssembly, then there is a lot of going back and forth between WebAssembly and JavaScript. So this overhead would definitely kill all the good things which are coming from the WebAssembly. It also consumes a significant amount of memory as of today. So the smallest possible amount of memory that you can pass to the WebAssembly module is 64 kilobytes. But it enables the serverless architecture, so as I mentioned, this attempts about the global computer. But what I think is more important, or the most important, is determinism and predictability, especially as compared to the JavaScript or the garbage collected languages or the dynamic languages. It has two formats. So it has a binary format, which is to be transferred over the wire and then executed by the runtime. And it has a text format, which is a human-readable form. If we take the canonical example of add, and here is the super simple code, which is just taking two integers, adds them together, and returns the result. This is equivalent to this WebAssembly text format, which is like a Lisp-like an S expression tree. So we see that this is just a module, and then we have the function add. The dollar means that everything following after it is a name, so this is an identifier, two parameters, and the result. And the actual job is done here. So the get local, it takes the parameters, puts them on the stack, and then invoking of this i32.add, it takes these values from the stacks, adds them together, and push the value again to the stack. Export is important because if we want to see this function from the outside, so if you want to call them from the outside, you need to export it. Otherwise, it stays local or private, shall we say. And if this is directly transferred to the binary format, then it looks something like that. So this is really looking like a bytecode or this assembly code. Nothing to do here as long as you're not going to run a heavy DSP processing, which web is anyway bad choice for that. So this spans over 2 pages for the simple functions that I presented. And I use there integer types, and this is not a coincidence, because as of today, WebAssembly supports only 4 types. So this is the 2 integer types, 32-bit, 64-bit, and 2 float types, 32-bit and 64-bit. And this is not the problem as for a C++, because we have pointers, these things can be emulated. But it's a problem if you want to interface with the WebAssembly module, because if the data type is something more sophisticated than an integer, than what one needs to do today, it's in JavaScript you need to allocate or create a linear memory, and this memory must be imported by the WebAssembly module, and then it can be used inside of it. Another problem is that for today in WebAssembly there is no access to the DOM, so to the document object model for the HTML for the web. So it's not frictionless. There is a lot of things going if you want to use a WebAssembly module from the JavaScript. Everyone talks about the performance, so let's look into the performance, especially when compared ASM.js with WebAssembly. So on the long run, we can say that WebAssembly can be somewhere between the native speed and the ASM.js. And ASM.js is like half the native speed. But the key point is that it doesn't really matter in the most cases. Because what matters is threads and assembly operations, which are game changers. These days, they are still experimental. They are not yet supported for all the browsers. But once they are supported, then we are talking about not speeding up by 10% or 20%. And nobody, by the way, cares in the web about this 10% improve. But this is an order of magnitude if we use threads and SIMD instructions together. So this is really something big. We also need to understand how the modern web engines are working, or how they are optimizing the code. So for the WebAssembly, we need to compare it to the JavaScript. Here I have an example of the V8 engine, and this is the Google engine, which is used by Chrome and also by the Node.js. So if it's about the JavaScript code, when the JavaScript code is available, then it is passed to the ignition interpreter. And what this does, it goes over the code, it interprets or executes the code, and along the time when the engine sees a hotspots or the hot functions, it takes these hot functions and passes to the turbofan optimizing compiler. Then this is optimizing this code based on assumptions on the parameters that he saw so far. When he's done, he's passing by the optimized code, and then this is executed. So that's why JavaScript is not that bad on the long run. However, when the assumptions made by engine or by turbofan optimizing compiler are not holding anymore, so the set of parameters is changed, then the code gets de-optimized, and then we fall off the quick path, and the ignition interpreter kicks in again and needs to do the job. So JavaScript is fast when optimized by turbofan, but relatively slow when interpreted by ignition interpreter. And it cannot be actually predicted when turbofan optimizer will kick in or when the code gets de-optimized. So overall performance is good, but the standard deviation may be big. With the WebAssembly, it's a little bit different because we have a lift-off base compiler. When the WebAssembly code is available, then the lift-off takes it, compiles it, and this is a quick compilation without advanced optimization. And then the code starts to get executed by the engine. And simultaneously, at the same time, the code is passed to the turbofan optimizing compiler, which does the heavy optimizing. When he is done, the code is switched in the runtime, and from that moment, the engine is running only the optimized code. And note here that there is only one direction. So once the code is getting optimized, it cannot be de-optimized again. And thanks to that, the standard deviation is small. So once optimized, stays optimized, and this delivers the more predictable performance. There are further optimizations for the speed. So we have a cold start versus caching. So if you access a web service which has a WebAssembly behind it, by the first time, this binary WebAssembly binary is first downloaded, then compiled or simultaneously compiled, and then executed. But if you do this the second time, then the web engine already knows that it's already downloaded and compiled or cached, and executes this immediately, so there is no delay on a startup. Recently, they also enabled a streaming compilation, and streaming compilation here means that when you start to download the WebAssembly module, which is not super small, then once the first packet is reaching the engine, it already starts to compile the code. So if the internet connection or the network connection is not super fast, it is possible that when last packet with the binary is reaching the engine, all the rest is already compiled, which means that if we are lucky, there is no delay for the compilation. Okay, enough with the theory, and now how to get it running. Unfortunately, we as C++ programmers are used to the pretty simple tool set. So we have the C++ compiler, and as the output we get the binary, and the binary then just runs on the target. Nothing really difficult there as from the running it. For WebAssembly or web in general, this is more complex. So if we want to use the C++, then first we need to write the program, we need to have the source, then we need to have a tool which will produce a binary for us. So as of today, the most popular is the mscripten, and this can produce the WASM binary, but the WebAssembly itself is not really usable as long as you don't have a JavaScript glue code for that. This can be generated by mscripten too, but it's not the best solution for the production code. And this is the web page, so we need to have at least some very basic HTML code. After having all these pieces together, it can be run on these 4 browsers. Going back to the simple example of add and save it to the add C. Assuming that we have mscripted installed on the system, it can be already compiled to the WASM binary. So with this command line, we get the binary. Note here this side module equals 1 flag. This means that the compiler will only compile what's inside in the source, which we pass here. Because by default, mscripten also compiles the system libraries. The good thing is that the binary is small. The bad thing is that you cannot access like a memory allocation or streams anymore. But for this example, we want to be as close to the bare metal as possible. And this may or may not work, because there is one more flag which is missing. And this is the exported functions. Maybe you remember in this text format I showed you also that we need to export the function. But it is up to the compiler, if you don't explicitly say which functions you want to access from the outside, to inline the function or to simply remove it as a dead code. And for C code, this is pretty simple, because the name of the function, it is add, or it is preceded by the underscore. But for a C++, this is getting more and more complex, because we have a name mangling. So actually, you don't know what compiler will do and what kind of name you should use here. So if not using any additional tools, this is the maintenance hell. There are tools which are supporting this. mbind is a good example for that. And about the output, I tell mscripten here to generate the binary, because if I don't say it, then the mscripten by default will generate for me also the JavaScript code and glue code and the HTML example page. Here I want to craft the JavaScript code, glue code by hand, and this is, I think, the simplest possible JavaScript code that can work with WebAssembly. So what we do, we instantiate streaming, so I make use of the streaming compilation already here, and with the JavaScript fetch, I fetch the file and pass the binary to instantiate streaming. What I get in the return is a promise with an object. And with this object, through this instance and exports, I can access my little add function. And then I can invoke it with some parameters, and I just print it out to the console. If I run it to the web browser, first I need to have some web server. mscripten comes with built-in simple web server, which can be run passing him that we don't want to use any specific browser, or we want to use this port like 8080. So once this is executed and I have the web server running, I can navigate to my local host port 8080, and in the web browser console I should see the result. And this is the result, so this is the proof that the WebAssembly code has been executed. So the conclusions, it's not friction-free. For this super simple example, let's see how much work I had to do, or how many pieces I had to put together to get it running. Tools like mbind, it can make it simpler for a C++, but still the name mangling is the challenge. Threads. I said that threads are not yet fully supported. As of today, I think they are enabled and shipped by default by Chrome. All the other browsers, they are either experimental or not yet implemented. And there's good reason for that the threads are lagging behind. Because in the background, they are using web workers, which is a technology for running a threads in a web engine. And the web workers there, they supposed to communicate between each other with a shared array buffer. And the shared array buffer is a JavaScript construct for a shared memory, easily saying. But the problem is that the shared array buffer and its API gives the possibility to construct a nanosecond timer. And we know from the Meltdown Inspector side channel attack that when you have the possibility to create these nanosecond timers, you can actually attack the side channel attack what's running on the processors and leak all the data. And web is all about security. That's why when it was announced that we have this possibility of these attacks, then the providers of the web browsers switched off the support for threads. So as from my Chromium browser, I need to go to the settings and I need to enable the experimental WebAssembly in order to get threads running. They give a nice warning that I can compromise security or privacy, but for the sake of the example and because we are running this only the local, that's not a big deal. Another simple piece of code. This time it's a C++ code. So I have just a function which is taking constref to the string, and it contains a loop which is looping 10 times and printing out this ID. Then in my main function I instantiate 2 threads, give him this function and pass him some ID. So when the threads are executed, then I can identify which one is actually executing. And then I wait until they finish, and I also finish the program. I need to compile it, so I use now in++. So because this is a C++ compiler, I need to enable a C++ 17 to get threads. I need to tell him explicitly that I use threads, and I need to tell him how many threads I use. So for my simple example, this is easy, this is trivial, because I know that I'm using 2 threads. But if you think about the more complex application where you don't really know how many threads are running in advance, this is getting more and more complicated. How many threads you want to predict how many threads you will run already on the compile time. I already tell him that this time I want to have JavaScript code generated for me by the compiler, but still I will give him, or I will create HTML file manually by hand. Because HTML in this case it's super simple. I just run the script, the JavaScript code, glue code, which is generated by mscripten. Then I run the browser or the web server, and from that moment I can access this service, this page, and I should see in the console that threads have been executed. We see here that they are in fact interleaved, so something has happened, so they were running in parallel. So that's a good thing. Note that with this generated JavaScript glue code here, it's more than 260 kilobytes. And that's the problem, because this must be then pushed through the wire. That's why I said at the beginning that the glue code generation, automatic generation, might be good if you want to just start up. But if you want to deliver something for the production quality, that's probably not the best choice to go for the generated glue code. And exceptions. By default, compiler, so mscripten, will transform all the throws to aborts. This means that your program will run, but it will terminate on the throw. And now if your C++ is using exceptions for exceptional things, this could be acceptable, or may not be acceptable if it's not using it just for exceptional errors. And by default, if you run a program which throws, a web browser will finish it, will terminate it, but it will also give a hint what to do if you want to have exceptions to be catched. So I need to add a new flag to my compiler command line, which I do. So I pass him the disable exception catching equals 0, and from that moment the exceptions will work, so they will be catched correctly. This comes with a price, so it's not cheap. Without exceptions, if we compare the size of the WebAssembly module, this is just above 160 kilobytes. And this is a very simple example which I compiled here. So what it does, it just executes the dumb code and throws. But with exceptions, it's already more than 270 kilobytes, so it's roughly 40% more. That's why by default exceptions are actually disabled in mscripten. Debugging. Of course, it would be nice if all the code we write has no errors, no bugs, and always runs correctly. That's not the case, as we know. And debugging in a web browser, this is always a challenge. This is always a struggle. There is a support by source maps. And source maps is again a JavaScript technology to mapping what the web browser is seeing to the original source and display it in a web browser so that you could debug this original code in the web browser. This is a little bit hacky because we are hijacking here a JavaScript specific technology and use it for a C++, though it works. And Firefox is generally better than Chrome in debugging. That's what I noted. If you want to debug code, you need to compile it with another set of flags. So first you need to pass him the -G4, and second you need to tell to the source maps where your source is actually living. So the web browser or engine can go for that and fetch it and then render it in your web page. I run it only on my local host, so that's what I pass him, localhost port 8080. And this is a simple code which is calculating Fibonacci numbers. Once this is ready, and once I have the web server running, I can navigate to my localhost 8080, assuming that I also have the HTML file. And this is what the console or debugging console in the web browser will show me. So it is showing the real C++ or a C code, and it is possible to stop with a breakpoint and then go over it. However, this is working more or less for this very simple code, but the more complex is the code, then less reliable the web browser debugging is. So in principle, this is more for the moment like a toy. So you can look, but if you have a serious problem, then probably you want to search for another solution and do not debug it in the web browser. Having said that, this is still work in progress. So as of today, a WebAssembly is released with the version 1.0, which is an MVP, and there are many of missing or experimental features. So there are no threats, there are no exceptions, or they are experimental. SIMD support is missing, and the DOM access is also missing, which is making then this very hard interoperation between HTML, JavaScript, and the WebAssembly module. And again, in my opinion, threats and SIMD support, this would be the biggest step forward. So once we get this enabled by default in all browsers, then we probably start to see or hear about WebAssembly more often. Until then, it's probably going to be still a niche. So there are a lot of things coming. They are working on that. I mean, web browser vendors. So stay tuned. And if you have any possibility or resources, then please try to spread the fame of C++ in the WebAssembly world. Thank you. If you have any questions, then you can ask them now or later.
This M++, is this based on Clang, or on what compiler is it based on?
Yeah, it's a Clang and LLVM. So actually mscripten it's an old project. It's already a 10 years old project, and at the beginning it was by default compiling to the ASM.js, and now they are shipping that they are compiling by default to WebAssembly. Mm-hmm. But this is LLVM plus Clang.
And this textual format you've shown, this is something like the intermediate language that can be generated.
This is the representation of the binary, a human readable representation of the binary. So this is, you can write it by hand, and then you can turn it into the binary, but it's not recommended or it's not intended to be run or to be written manually, but you can do it in principle.
Any further questions? Okay, so thank you very much.
Thank you.